Log on, tune in, find out. Another good idea from Cambridge.
Homotopy type theory and structure identity.
I gather I'm supposed to say how long I'm going to be here. I'm going to be here for quite a while, till towards the end of March, and then I'm coming back again for most of the month of May. When I first arrived, I think in the second week of the program, I gave an unadvertised 5-minute talk on on the kind of topics I hope to do here, but probably many of you weren't here then, so I'll have a slide where I give an idea of my research interest in in many years. So, I have for many, many years been interested in constructive set theory and dependent type theory. I have only rather recently come to be interested in homotopy type theory, which is what my talk is going to be about. But let me just say a few words about the first two topics. In some sense, constructive set theory and dependent type theory are very closely interrelated. There's an interpretation of sets as trees of constructive set theory into dependent type theory, which was obtained in the 1970s. And there is a very straightforward types as sets interpretation of type theory into set theory. You can simply interpret types as sets. In contrast, homotopy type theory is concerned with another kind of interpretation of type theory, not into sets, but something more complicated involving homotopy, ideas from homotopy theory. Another topic I'm interested in, which is related to these, are categories for dependent type theory, syntax and semantics. In the literature, there are many notions of category for dealing with the semantics of dependent type theory. One can also use those semantics to deal with the syntax of dependent type theories, but I've been always rather unhappy with that, and so I've introduced my own notion of generalized type setups, which is something I have preferred. So that's another topic that I've been interested in. So let's go to the topic of this talk. So here's the plan. You see the number of slides. Something like this talk I have given in the past, where I had longer than 30 minutes, and so I gave a review or introduction about dependent type theory. I don't have time to do that today, so I'm going to try and give you some idea about homotopy type theory without telling you anything much about type theory. So I'll hope that be successful. The way I'm going to do it is via the structure identity principle, where there are 3 slides on. Yes, so if there was time, there will be topics 5 and 6, which would be a review of type theory and a precise definition of the univalence axiom, a key axiom to be added to dependent type theory, which would give rise to something like the structure identity principle. If you're interested in homotopy type theory, there's a lot on the web. So if you Google appropriate keywords, you'll find a lot of information about homotopy type theory. Okay, this is a relatively new subject. Voevodsky and Awodi were the independent originators around 2005-06 of the ideas at the basis of homotopy type theory. It's an amalgam of higher dimensional groupoid category theory, homotopy theory, and type theory. Now, I'm pretty familiar with various formulations of type theory and its syntax and semantics, but I must say I'm pretty unfamiliar with homotopy theory. It's a new subject for me, which I'm desperately trying to learn about at the moment. So I'm not going to go into any details about the motivation for homotopy type theory coming from homotopy theory, but from this other idea of structure identity principle, which I hope will mean something to you without going into homotopy theory or into type theory. Okay, as I mentioned, the univalence axiom is an axiom introduced by Vygotsky to be added to dependent type theory. And he puts it forward as a new approach to the foundations of mathematics. So I'm going to focus on an application of the univalence axiom, which I'm calling the structure identity principle. In one of the very early talks, which I only discovered fairly recently, of Vygotsky, he does motivate his univalence axiom from something like the structure identity principle. I came across this principle through seeing some slides of Thierry Coquin. The terminology structure identity principle is my own. I think there may be other terminology that people are using. Okay, so one of the ingredients of homotopy type theory is higher dimensional category theory. So the idea here is that there's a hierarchy of different notions, starting with sets, which are things which can have elements, things in them, categories. So if the elements of a set are called objects, then categories also have arrows between those objects. Going up one dimension further, two categories have in addition arrows between those arrows, and so on into higher dimensions. So that's an initial idea about higher dimensional category theory. A lot of work has been done on higher dimensional category theory in the last 10, 15 years. It's not a topic I'm that familiar with. So there's also the issue of identity between elements, and this changes as you go up in dimension. So we have the usual notion of identity between the elements of a set, but when it comes to the objects of a category, category theorists say that when you're looking at categories of structures, the right notion, you don't want to distinguish between isomorphic structures. And that's the first glimpse of what the structure identity principle is about. When we go to a dimension higher, isomorphism is no longer the appropriate notion, and it turns out that a two-category, like the two-category of categories, the appropriate notion is equivalence between categories, or in a general two-category, equivalence between the objects of the two-category. And again, you can go up in dimension. So that's a slide giving you a little bit of a flavor of high-dimensional category theory to the limited extent that I understand it. Okay, in a category, you have associative laws up to equality. There's a weak notion where you weaken in the higher dimensions of the notion of category, where you don't require the identity and the associative laws that you usually have in a category, but you use an appropriate notion of equivalence rather than any notion of actual, any kind of equality. A groupoid is just a category where every arrow has an inverse, so every arrow is an isomorphism. And there's a weaker notion of high dimensional groupoids which play an important role in homotopy type theory. Just a few words about homotopy theory. So in homotopy theory we have a notion of space with points, paths between points, and homotopies between paths. So paths between paths, and you can go up again in dimension. So there's some kind of parallelism between, or analogy between homotopy theory and higher dimensional category theory. And it turns out there's also parallelism in the context of dependent type theory, of having high dimensional things. So in homotopy theory, with each space is associated the set of its path-connected components, and then at dimension 1 there's the fundamental groupoid. Traditionally, one talks about the fundamental group, but groupoids are much better in modern homotopy theory, it seems. And there are the high-dimensional groups, or here, the high-dimensional groupoids. So these play a role, the intuitions about this play a role in homotopy type theory. In homotopy type theory, there is an important notion of weak equivalence in the context of type theory, and this is motivated by a notion of weak equivalence in homotopy theory, which is saying that a continuous function from one space to another is a weak equivalence if it induces isomorphisms on the higher dimensional, on all the groupoids. So I'm just mentioning that here. Okay, so homotopy type theory interprets types no longer just simply as sets, but as something like spaces, or it might be more accurate to talk about homotopy types of spaces, but I don't want to go into that, so let's just say it's spaces for the moment. And in type theory you have something called identity types, and these get interpreted as path spaces, the spaces of paths between points. What I'm listing on this slide are some of the ingredients of homotopy type theory. So I'm not going to have time to explain any of these, or I'm only going to be explaining one of them. There's a notion of higher dimensional inductive definitions of the standard spaces. So for example, one can give on about 3 lines a definition in homotopy type theory of the circle, and prove in homotopy type theory that the fundamental group of the circle is the integers, as it is traditionally. So there's a very simple definition in homotopy type theory of the circle. It involves something called a higher dimensional inductive definition, which is a very new idea. It's only about a year old. And I'm not sure at least I don't claim to fully understand how to make sense of higher dimensional inductive definitions in type theory. So it's one of the issues. Sorry? One of them is Peter Lumsdaine, if you know him. There was an Ober-Wolfach meeting I was at about February last year, and the idea came up there. It was Peter Lumsdaine and 1 or 2 other people, probably Steve Awodi, but I'm not sure. Another ingredient of homotopy type theory is that there is this hierarchy of higher dimensional types going on. At the bottom, well, at one up from the bottom, but I won't go to the absolute bottom, are what in some sense play the role of propositions. So in some sense, in some aspect of logic is occurring at the bottom level. The notion of set is occurring 1 level up, then you have groupoids, 2 groupoids, and so on. So within type theory, you have the same kind of hierarchy analogous to what you have in high dimensional category theory and in homotopy theory. Then there's the univalence axiom and the structure identity principle. So this is where I'm going to spend the rest of the slides on. talking about the structure identity principle, and that the univalence axiom entails that this holds in a very strong way in homotopy type theory. There is a model of simplicial sets, of homotopy type theory, using simplicial sets. So it gives there's a model of type theory where the univalence axiom comes out correct, and almost my last slide will say something about that model construction. Vygotsky is very highly motivated to do machine-checked mathematics, and he is using the Coq proof development system. So most of homotopy type theory is done and machine-checked in Coq. Some of it has been done also in the proof development system at Agda. In one sense, this is a good idea. It's going to put, I believe, proof development systems much more on the map. On the other hand, I think it's a rather bad idea to exclusively just do machine-checked mathematics. I think one needs to do informal mathematics in the usual style of presenting mathematics. So one of my motivations is to try and, first of all, understand what's going on in Coq about homotopy type theory, and put forward a style for doing informal homotopy type theory. This is a problem because it's doing mathematics in type theory, and we're used to doing mathematics in set theory, but not in type theory. So one needs to develop a tradition for doing mathematics in type theory, informally. Okay, so here's the principle. Isomorphic mathematical structures are structurally identical. I assume everyone believes this. I have the same structural properties. But of course, what do we mean by structural property? Well, here's the principle, first of all. If A and B are structures of the same signature that are isomorphic, then they are structurally identical. In other words, any structural property of one structure is also a structural property of another structure. Okay, if there's any reasonable definition of structural property, you surely believe this principle. I'm not being precise of what I mean by structure. It should apply to any sort of reasonably sensible structure. So what is a structural property? So I claim in mathematical practice the notion is usually not precisely defined, but we understand what it means, I claim. But in logic we can give a precise answer. Choose a language for your structures, appropriate for your signature, and take a set of sentences in that language. Then we can form the structural property of a structure A, that A is a model of the theory, of the set of sentences. And as we know, isomorphic structures have satisfy the same sentences of any reasonable logical language for the signature of that structure. So there can be a variety of different kinds of languages, and in that way we get structural properties. In category theory, when working with a category of structures, I think I've already mentioned this, equality between objects is considered not meaningful. So the appropriate language to use when talking about a category of structures is a category where the only notion of equality between objects is isomorphism. And the language can only talk about structural properties. No other properties make sense. Okay, so homotopy type theory at present is simply some version of type theory, And I prefer Martin Luth's approach to type theory rather than the type theory implemented in Koch, which is very impredicative. But take a reasonable intentional dependent type theory and add a univalence axiom. So it turns out that in homotopy type theory, with the univalence axiom, isomorphic structures are actually identical. In the type theory, there's the notion of identity of types and identity between the elements of any type. And the univalence axiom gives this principle. So in homotopy type theory, you cannot, well, you have this principle. So you can only express structural properties of structures. So we have this principle. If C is the type of structures of some signature, then if A and B are isomorphic structures, then A is identical to B. And I've used this funny notation because the notion of identity that we have in type theory turns out to, in homotopy type theory, to play the role of the type of paths from A to B, or down here. In general, if we have a type X and two elements of the type X, then we can form this type, which in traditional type theory you would write as the identity type for X and X prime. But here, in homotopy type theory, it plays the role of the type of paths from X to X prime. So thinking of types as some kind of notion of space, we have this notion of path. And the seemingly, at first, miraculous thing is that the usual notion of identity types that we're used to in type theory turns out in homotopy type theory to be just exactly what can play the role of the path types in homotopy theory. So this is really remarkable in my view, and indicates that there's something rather deep going on. Okay, so the type theory with the univalence axiom is consistent. So Vygotsky has a proof that the univalence axiom for a type universe U can hold when you interpret type theory in the category of simplicial sets in a suitable way. Unfortunately, from my perspective, it requires classical reasoning. So his proof, as far as if one looks at it, uses ordinals, the axiom of choice, and the Grothendieck universe. Well, the Grothendieck universe is reasonably natural to use because univalence axiom is an axiom about a type universe. In type theory, there is a notion of universe one can have. Okay, so I'm hoping to understand the proof, but it does require me to learn more homotopy theory than I've done so far. Here's a question that would interest me a lot. Can a model construction be carried out in a constructive meta theory? I feel it ought to be possible, but at the moment I've no idea. Okay, so this is almost my last slide. It looks like it is. Some examples of what this univalence axiom gives you. If you take two types in the type universe U, the univalence axiom is saying, in a very strong sense, that if A if the two types A and B are in bijective correspondence, then they are identical in this sense of identical. Maybe one should put identical in quotes, because obviously the standard type theoretic notion of identity is somehow is a much richer notion in homotopy type theory than we're used to thinking about it in ordinary type theory. But we can look at more complicated structures. So the first thing, saying that A and B are isomorphic types, a type is the most trivial kind of structure you can think of in type theory. But let's consider a structures with a distinguished element, a type with a distinguished element. So you have the same thing there, where now we're looking at structures in a type C, which is defined as a sigma type, which consists of pairs consisting of a type in U paired with an element of that type. Okay, so it follows from univalence axiom that isomorphic structures of this kind are identical in this type theoretic sense of identity. And here's a more complicated example still with a billion groups. So you have the same thing. Right, now I did have a final slide, but something went wrong with my slides at the very last minute, and it seems to have disappeared, unfortunately. So my final slide was a list of some problems or issues. So maybe I can try writing on the blackboard if I can remember the issues. Well, one issue is type theory itself, at least the Martin-Löf version of type theory itself, is very weak compared with Zermelo-Fraenkel set theory. Now, adding the univalence axiom, the model construction for the univalence axiom seems to require a very strong ZFC plus a Grothendieck universe. So a key question for me is, what is the logical strength of homotopy type theory with the univalence axiom? I would like to think that it's not much stronger than dependent type theory itself. And therefore, there should be a much more constructive model construction. But I certainly don't know that. So that to me is an important question. My mind is a bit of a blank at the moment about I had a list of about 8 problems. If you're interested in seeing the list of problems, please send me an email and I'll send them to you. But I think I'd better stop there.
Any questions?
So Martin-Löf type theory is a very good, sophisticated construction where everything has computational content. So the objects are computational objects, and then you define the functions, and you have a very natural way of getting the elimination rules from the reduction rules, etc. How does this univalence axiom fit into this? Does it destroy it? Or is it some kind of natural?
Voevodsky is very concerned to keep the computational content, but I think it's still an open question for him. That in some sense he wants to retain some aspect of the computational content you have with dependent type theory usually. But as I said, I believe it's an open issue, but it's a major preoccupation, I believe, with him.
Yes.
Yeah. The univalence axiom. Is it possible to give us an idea what it says? I mean, I guess it must be hard to state.
Well, I said it, so.
It has this implication. Oh, I see. Is it
it's much stronger than just having a logical implication. It's saying that the type A isomorphic to B as a type is weakly equivalent to the identity of A identical to B. So weak equivalence is much stronger than logical implication. So that first line there is giving a reasonable indication of the kind of thing it is. It's something stronger, it's a very strong sort of implication, which only makes sense in the type theory context.
Actually, I'd like to ask. Actually, I heard a talk by coincidence yesterday by Kobe Kosmitsa, who was in Oxford, and he was very much selling this as a new language for mathematics. This was the title of his talk.
I didn't catch the name.
I can't remember the last
Okay,
name.
doesn't-
Kobe Kosmitsa. I don't know if anyone's. He's in Oxford.
Yeah.
And so when he was talking about, so my assumption is that the proofs that are going on and that are being actually done in Coq and so on would be constructive proofs. Is this saying that we're solely, well, I won't say limited, but we are just using constructive proofs when we're talking about...
I think on the whole, Voevodsky and other people are doing things constructively. I mean, the logic is, well, I haven't got into how logic is being treated here. It's roughly propositions as types, but it's a bit more complicated than that.
So he seemed to be a little bit unclear about what the logic was of these kinds of arguments, but one thing he wanted to emphasize was that this apparently gave one great speed up in terms of proofs. He was saying that with an interpretation in set theory, everything is hard, and whereas the interpretation in homotopy theory, one can reduce things to sort of two-line proofs or three-line proofs. There's a lot of speed up in terms of simplicity, and this was one of his.
Well,
selling
for
points.
example,
do you have any comment
the
on
proof that the fundamental group of the circle with the homotopy type theoretic definition of the circle, whether it's that much shorter than the usual one, I don't know. But it doesn't require talking about the real numbers in the usual traditional way. You have this 2 or 3 line definition of the circle, and then there is a proof done in Coq, so it's been machine checked, that the fundamental group of the circle is the integers, and I don't think it's very long, but whether it's much shorter than, in some sense, than the usual one, I don't know. Can't say.
In the context of that, though, do you then need to use the real line in the usual way to show that this definition of the circle has it defines a model?
I haven't seen that done, but it's, I know for some months Voevodsky has been working to do normal mathematics in homotopy type theory, and obviously that would eventually lead to trying to answer that question. I don't know how far he's got. I have struggled with getting to grips with Coq, so I haven't read all the stuff that's been going on.
Okay, perhaps we should stop there because we're out of time. But thanks, Peter, once more.